Hi everyone, we are back and we are going to do our Pset 5 solution video. So this is the last problem set before your exam. So let's look at the problem. So first, label all the invariant points, indicate what type they are. Label all the regions of the phase diagrams, congruent melting points. So congruent melting points, we always know that there's two, one right here, and in this problem there's no other congruent melting points here. Let's label the phases. So remember, I'm in a composition here, I'm just going to go to left and right. So this would be liquid plus this phase right here. If I'm going here, it'd be this liquid phase here plus this solid phase AGTI here. If I'm here, it's going to be AGTI plus BCC. If I'm right here, it's going to be BCC plus AGTI2. If I'm here, it's going to be this plus this. If I'm here, it's going to be this plus this. If I'm here, this one's already labeled for us. And that's it. So you just want to kind of go left and right, see if you're touching a solidus, liquidus, and write out those phases. Now, we always know that if we have bunny rabbit ears, we have peritectic or peritectoid. Ick has liquid, so here we would be going from liquid to a two-phase solid region. If it's an oid, so it would be going from a single-phase solid to another two-phase solid region. Three distinct phases we need. And if it looks like a T or a cross, or if it looks like this with some width to it, that, excuse me, that's not peritectic. These are eutectic. Eutectic is bunny ears, and eutectoid as well. Peritectic is over here. Just testing you. I never make any mistakes. Everyone knows that in my classes. Oids, and then we go from here, again, it'll be a liquid plus some solid phase region to a single phase solid region, and then alpha plus beta goes to a gamma. So let's find it in this example. So here we have an invariant point. Actually, let's zoom in here so I can see clear invariant point right here. What is this? It's a liquid plus this BCC going to solid, so that is a peritectic. We also have another one here. I have a solid plus a solid goes to another two-phase solid region right here. So here we actually have a peritectoid. Additionally, you may kind of see a thin line here. This could also be basically a eutectoid as well. So again, this right here, or in that region, you can't really see the thin line, but it is connecting. So this would be a eutectoid as well. But I won't count that against any of you because, and you could do the same thing here with a eutectic coming into a liquid to two-phase solid region. But we can't see that in this diagram, so no points against you. I'm very generous. All right. Calculate degrees of freedom at 0.3 Ti and 500 K. So right here. So what are my degrees of freedom? D plus P equals C plus 1. Components are always 2. What are my phases there? 2. So my degrees of freedom is going to be 1. What about at 1500 C? Actually, that should be a little typo there. I'm going to call that K. And then 0.8 here. Same answer. Degrees of freedom is going to be 1. What's the maximum solubility of AG and TI? So when I'm at 100% TI here, I could fit about, let's call this 0.18 mole fraction of AG and TI. How much TI can I fit in pure AG? Not too much, only about, let's call it 0.05 mole fraction. Excellent. Now, what else are we asked to do? Okay, I have a sample at 0.4 mole fraction TI and about 400 K. So right here, what is the concentration fraction of all the phases? So I'm in two phases here. Let me try to draw a straight line. So I have some composition that's in my, basically, we'll call it the FCC phase, some concentration that's in the AGTI phase. To find the FCC, I just go all the way to the left, so that's going to be about 0. AGTI, go all the way to the right. That's going to be about, let's call it like 0.49. So those are my concentrations. To get the fractions, I have to use the lever rule so that I'm closer to the AGTI side, so I should be mostly AGTI. So the fraction of AGTI, remember I divide out by the total length, which is this 0.49 minus 0. And then I want to run to the opposite side. So it's going to be my concentration, which is 0.4, minus this side right here, which is going to be 0. And for the fraction of FCC, same denominator, 0.49 minus 0. And then in the top, I'm going to get the opposite side now, so 0.49 minus 0.4, my concentration. And that's it. Excellent. So now it says draw the free energy curves at a temperature of 1250 K. So let's do 1250. Let's say I'm right over here. Let's kind of erase a little bit for now. Let's erase over here. Then let's zoom in so we can kind of see what's happening here. So if I'm at 1250, I'm just going to draw my line across this, and I can kind of see where my isotherm, my temperature line is, and I can see where I start to kind of cross over into these phases, or these different phases here. So actually, I'm just going to draw it going straight up. That's here, that's here, that's here. This is a nice little trick that I typically use when I'm solving these problems. So I could draw it on basically the similar or same axis. So we're looking at free energy curves as a function of concentrations. We know that when I have two phases in equilibrium, my chemical potentials of those two phases, solid or liquid or solid-solid, must be equal to one another. And we know that we can relate the chemical potential to our common tangents or the slope of this free energy curve here at constant temperature and pressure. So when I have a two-phase region, like in here, where I am going to be basically a liquid plus an AGTI, and when I also am going to be here, I'm going to be AGTI plus BCC. And here's where I need to find my, here's where I need to get my different colors. So I'm going to probably decrease here. Yep, so I could get different colors. So first I'm liquid, so let's always keep it consistent liquid blue. So initially I am pure liquid phase right here, and then I am just going to draw out some common tangents that I'm going to have to touch. So I'm pure liquid, that's the lowest free energy, and then it kind of increases. AGTI, I'm going to keep that as red. So red is my AGTI. Initially it's higher, but when I'm in a two-phase region, I need to make sure that these common tangents have the same slope. So I have the same slope here, I'm still the lowest in here, and then I need to have another common tangent for this two-phase region here. So I could just draw that up there. And then for BCC, I'm going to make that green. BCC, and again the green is just very high energy here, and then again I need to hit that common tangent because in these two regions where I'm in that two-phase region, I need to make sure my common tangents have the same basically slope, so at those concentrations. So again, when you're solving problems like this, just draw out what are the phases at the different compositions, and then you'll solve the problem, and after that you're done. So that's it. All right, let's go to the next set of problems that's very similar, but give you some more practice. So again, we're going to ask to all the invariant points, congruent melting points, etc., etc., etc. You're experts at this point. Congruent melting point here, congruent melting point here. No other congruent melting points in this particular phase diagram. Here, I can see I'm going to add this plus liquid. This is going to be this plus liquid. This is going to be this plus liquid because we're hitting that. This little region is going to be this plus this. This little region here, because that's a single phase here, it's going to be this plus this right here. And then here it's going to be this plus this, liquid plus this, and we're hitting all those phases. This will be SN plus liquid as well. So let's erase that so that we can get going. My battery's running out. So let's go ahead and continue. So now I need to go ahead and take a peek at what are the invariant points. So this right here will be my eutectic because I'm going from a liquid to a solid region here, and then an Ag3SN solid region here. I'm also going through liquid plus solid goes to a new solid here. That's going to be a peritectic. I'm also going liquid plus solid here to a new solid. That's going to be a peritectic as well. So those are the only invariant points in this problem. Let's see what else we're asked to do. What is the maximum solubility of Ag and Sn? That's going to be basically 0. How about Sn into Ag? I could get probably about 10% of Sn into Ag. So we know what about the diffusivities are happening in here as well. So now I can go ahead and solve the rest of this problem. And let's go ahead and see. So we're looking at a sample of 60 Ag and 300 C. So what are the compositions and fractions? Or I've sampled 60 Ag and 300. Oh, there's my energy back, thankfully. So now we could solve the rest of these problems in full light. So I have 60 Ag, 300 C. So let's go ahead and put that there. 60 G, 300 C. So where are we? Two-phase region, as we can see here. Concentration fraction in all phases. So we have some concentration that's in liquid. That's around 0.10. Concentration that's in the Ag3SN, which is around 72. Fraction of liquid. So we're going to do, again, divided by the total length of that line, 72 minus 10. And then, let's see. So I am far away from liquid, so I'm going to go from 72 to minus 60. And then for the fraction of Ag3SN, which I'm closer to, that'll be the larger fraction, so it'll be 60 minus 10 over 72 minus 10. And we can do the math after that. Excellent. And then finally, draw the free energy curves at 600 C. So let's go ahead and do that. Let's, again, try to do our method we did last time. This will be a little bit tougher because we have this, but so at 300 C, or 600 C, excuse me. So 600 C, I'm going to draw it like this. So until here, I am pure liquid. Then here, I am two-phase liquid plus this is like eta. Then from this little region here, little tiny region, I'm pure. This little region there, I'm pure. Actually, that's a big region where I'm pure eta. Excuse me. So from here to here, I'm two-phase. From here to here, I'm single-phase eta. Then I'm a little tiny two-phase region here. Eta plus Ag, and then I'm Ag after that. So once I'm past that marker. So let's go ahead and start to draw some of those lines. So I have a common tangent. Let's just put it here and here. So I'm liquid here, and then I jump out and I'm gone. I'm going to put my eta. Eta is going to be red. So I start off here. I have the common tangent, and then in this sliver here, from here to here, which I'm trying to draw from here to here. So I have that common tangent here, and then the lowest, and there's going to be another super tiny common tangent, basically from here to here. Excuse me. Let me draw that. So another common tangent like this, and then this goes away, and then finally my Ag comes. And it is going to have, come down, it's going to hit that other common tangent. So remember, I have this common tangent where I'm eta plus Ag. I have this common tangent right here where I'm liquid plus solid, then pure eta here, and then I'm the lowest free energy curve. And that's it. So that is it for Pset 5 for spring 2022. So study this, look over your problem sets, and do well in the exam. And I will see you all on Monday. Thanks. Bye.